Welcome back. In the last lecture, what we have seen is that the family of P r theta, which is defined to be summation r to the power mod n e to the power I n theta. So, this satisfies all the three properties of being a good kernel. So, this P r theta is called Poisson kernel. And exactly for following the proof of the good kernel convolved with f converges to f at the point of continuity, exactly following the same proof, what we can get is this is f 2 pi periodic Riemann integrable if f is continuous at theta naught, then f convolution of P r at theta naught goes to f of theta naught as r approaches to 1. Moreover, if f is continuous everywhere, then the convergence is uniform. So, now here what is the picture? Actually, if we are looking at f r theta naught, then f r theta naught, if we are writing it as a function f r theta, this is equal to f convolution of P r of theta. So, then this is kind of defined inside the unit disk, because for each r and theta here. So, this capital F is defined on inside the unit disk. Now, when r approaches to 1, that means what we are saying, that we have a function on the unit disk. When we are approaching to the boundary of the unit disk, that is the unit circle, what kind of function we are getting. If we are dealing with the Poisson kernel, then we, if f is a continuous function, then we are going to get back the f defined on the boundary. So, f is a 2 pi periodic function, therefore, f is defined on, we can imagine that f is defined on the boundary, that is on the unit circle, and we can get back that f if the inside the capital F is f convolution of the P r. Now, this suggests us to define the following, another way how one would sum a series, because everything. So, essentially what we are saying is that in the terms of the Fourier series, now if you look at the Fourier series of f convolution of P r theta, if I take the Fourier transform at n, then this is equal to f hat of n and e to the P r hat at n. Now, P r is r to the power mod n e to the power I n summation. So, therefore, P r hat at n is equal to r to the power mod n. So, what essentially the of we are saying, the Fourier series of f convolution of P r, Fourier series of e to the power I n t. Remember that this series is absolutely summable, because f hat is a bounded function r to the power mod n, r is less than 1. So, at So, now what we are saying that Fourier series may or may not converge for f, but in this term they are converges. So, this suggests us to define Abel summability is a series of complex number k equal to 1 to infinity, 0 to infinity, you can take that whatever you want, is said to be Abel summable to S if for each R A of R, which is defined to be k is equal to 1 to infinity C k R to the power k exists, is summable. That means, the series C k R to the power k, that is a convergent series, and not only this, because you can see that C k R to the power k is a convergent series for any C k to be any bounded sequence, because if I take the bound, then this is dominated by a geometric series of R to the power k, and we know that that is summable. But this is importantly, it is Abel summable if limit r goes to 1 minus a r exists. Okay. So, as we said a while ago, that if mod C k is less or equal to some m for all k, then is a convergent series. But that does not mean that A r exists, that does not mean that limit r goes to 1, A r is going to exist. So, now for example, take C k to be constant sequence 1, then summation over C k r to the power k, if I write k equal to 0 to infinity, then this is equal to 1 by 1 minus of r, and which does not converge as r goes to 1. So, now we need to take the extra care to check in order to get that this is Abel summable, that limit r goes to 1 exists. But there can be some unbounded sequence C k can be unbounded, still A r is going to exist. For example, let us take C k is equal to k. Then what is going to be our A r? K r to the power k. So, now this I can write that this is 1 over r summation over k from 1 to infinity k r to the power k minus of 1. Now, you consider B r to be summation k is equal to 1 to infinity r to the power k. This is a absolutely summable series, therefore, B prime of r this is equal to summation k from 1 to infinity k times r to the power k minus of 1. Now, B r we know that this is equal to 1 by 1 minus of r minus of 1. So, this is equal to r by 1 minus of r. Therefore, this quantity is nothing but 1 by r d by dr of r by 1 minus of r. So, this is going to be 1 by r, this is 1 minus of r square, and then this is 1 minus of r minus of r plus r. So, this is 1 by r into 1 minus of r square, which does not converge. Now, here even for the bounded sequence A r k exists, but limit r goes to 1, A r may not exist. So, however, if we look at the C k, if we are taking this to be minus 1 to the power k, k plus 1, then A r, this is going to be summation over k from 0 to infinity minus 1 to the power k, k plus 1, and then r to the power k. This of course, is converges, because r is less than 1, you can use the ratio test or what not, and you can get that this is going to converge. Okay. So, now what is then to find out what this A r, exactly following this step, if one can get basically that if we are taking B of r to be 1 by 1 plus r, that is equal to 1 by 1 minus of r, then there is going to be, when you are taking to the power k, then this is going to make minus 1 to the power k is going to appear in the geometric series in the expansion. So, therefore, this basically what we are going to get, this is going to be B prime of r. So, A exactly like before, this is going to be 1 by 1 plus r square. Now, this converges. Now, this is the series. If so, this series is Abel summable clearly this is not summable. So, now what we are getting is that there is a series which may not be summable, but it can be Abel summable. Exactly what we got, we have seen that the series may not be summable, but it can be Cesaro summable. Here another thing what we are saying, it may not be summable, but Abel summable. It is natural to ask that whether this particular series, is this also Cesaro summable? So, now, so is now, if any series is Cesaro summable, suppose if let us say is Cesaro summable, then what do we get? We get that the sigma n, that is sigma n, which converges to sigma. So, that means what we are saying, sigma n, recall that this we are taking to be S 1 plus S n. If I am taking n equal to 0, then this is n plus 1, or if I am not considering 0, then this I can go up to n. Therefore, n sigma n, this is equal to S 1 plus S n. Therefore, n sigma n plus 1 minus divided by n plus 1, this is nothing but S n plus 1. Oh, sorry, this series we can take it as a S n plus 1 divided by n plus 1. Now, as you can see, sigma n converges to sigma, therefore, sigma n plus 1, this converges to sigma, and n by n plus 1 converges to 1, and sigma n converges to sigma. So, this is equal to 0. Therefore, what we conclude, remark, if summation over a n converges is Cesaro summable, then a n by n goes to 0. If sigma a n summation over a n converges, then we know that the necessary condition is that a n goes to 0. If it is Cesaro summable, then the necessary condition is a n by n goes to 0. Now, coming back to our series this, so therefore, minus of 1 to the power k by k plus 1, this divided by k. So, this does not go to 0. Hence, it is not Cesaro summable. So, now natural question now comes. Here we have a series which is Abel summable, but not Cesaro summable. Now, natural to ask, is summable will imply Abel summable? That is quite natural. If I have a convergent series, is it going to be Abel summable? In the similar way, one can ask that Cesaro summable, is it going to give Abel summable? So, now theorem, summable will imply Cesaro summable, and this will imply Abel summable. So, if we can show only this Cesaro summable is going will imply Abel summable, then if it is summable, it will be Cesaro summable, hence it is going to be Abel summable. And as we have seen, the reverse direction does not hold, because we can get a, we know that there exists a Cesaro summable series, namely minus 1 to the power n, which is not summable. And we have got an Abel summable series minus 1 to the power n, n plus 1, which is Abel summable, but it is not Cesaro summable. and neither it is Caesar summable nor it is summable. So, the reverse direction is not true. So, now let us try to prove that Caesar summability will imply Abel summability. Okay. Now, in order to do that, so let us let sigma n converges to sigma, then we want the series what we are given is C k, sigma n converges to sigma, we want limit r goes to 1 minus a r, this is equal to sigma. If we can prove that, then we are done. So, first let us prove for sigma to be 0. Then we will show that does not matter if sigma n converges to some sigma which is not equal to 0, then we can manipulate our series C n by taking a d n, which from this result we will get the other one. So, now in order to show that A r converges, that means and we have given the data that it is Caesar summable. So, we are interested to find the expression for C n r to the power n. This is what we want to. So, now if this attempt should be, now we should try to write C n in terms of sigma n. So, how we are going to do that? Now, what we have seen is that the sigma n times sigma n, this is equal to S 1 up to S n. This is the nth partial sum what we are taking. Now, therefore, first we look at this identity for you take n greater or equal to 3, n sigma n minus 2 times n minus 1 sigma n minus of 1 plus n minus 2 sigma n minus 2. So, this is going to be equal to, you have S 1 up to S n minus 2 S 1 up to S n minus of 1 plus S 1 up to S n minus 2. Now, the for S 1 to S n minus of 1, this is going to get cancelled. So, now in this I have got S n. Now, I have minus of S 1 up minus of S 1 plus S 2 up to S n minus of 1 plus S 1 to S n minus 2. So, here this would be S n minus of 1 which is equal to C n. So, C n can be expressed in terms of sigma n. Therefore, we write the summation over C n r to the power n, this is equal to, I can replace this as summation over n equal to 1 to infinity n times sigma n r to the power n minus 2 times n equal to 1 to infinity n minus of 1 sigma n minus of 1 r to the power n plus n equal to 2 to infinity n minus 2 of sigma n minus 2 r to the power n. Now, this is equal to, I can write this summation over n equal to 1 to infinity n sigma n r to the power n minus 2 into summation over n equal to 1 to infinity n sigma n r to the power n plus 1 plus summation n equal to 1 to infinity n sigma n r n plus 2. So, therefore, this is equal to summation over n from 1 to infinity n sigma n r to the power n. If I take it common, this is minus 2 r plus r square, which is equal to 1 minus of r square summation n equal to 1 to infinity n sigma n r to the power n. Now, we are interested for r goes to 1. If we can control this, then limit r goes to 1, this is going to give us 0. Okay. So, now what we know? We know sigma n converges to 0. That means, for epsilon positive, there exists a n sub naught such that mod of sigma n is less than epsilon for all n greater or equal to n sub 0. Therefore, mod of summation over n from 1 to infinity n sigma n r to the power n, this is lesser equal to, I can get that n equal to 1 to n naught minus of 1 n sigma n r to the power n plus n mod of sigma n and then r to the power n. Okay. So, now in the second term, this is, let us call this as I 1 plus I 2. Now, as you can see that I 1 into 1 minus of r square, this of course, is going to 0 as r goes to 1, because that is a finite sum. And now, for the other one, the second one is less than epsilon into, as what we have done, d by dr of n equal to n naught to infinity r to the power n. And that is, of course, is a geometric series, which you can write it down in the terms of the this is n naught r to the power n naught minus 1, or basically this is lesser equal to, with a little bit of algebra you can show that this is lesser equal to epsilon times n naught. So, that is small. Therefore, this entire 1 minus of r square, if we are doing it, so this goes to 0. So, this entire thing is going to be, it is small. Hence, A r converges to 0 as r goes to 1. Now, if sigma n converges to some sigma which is not equal to 0, you consider just this is the series minus sigma by 2 to the power n, then this series is summable to Cesaro summable to 0, because C n is Cesaro summable to sigma, and you have the previous earlier result, that if sigma n converges to 0, then AR will converge to 0, and that will guarantee that in this case the AR is going to converge to sigma. Okay. Thank you.